Warning, the video you're about to watch contains mathematics at the level of pre-calculus. All material has an assumed prerequisite of college algebra and trigonometry. While some prerequisite topics are reviewed briefly, a more thorough review of these entrance topics can be found by searching the web.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook over.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is meant as a review of concepts for your trigonometry class, or from your trigonometry class. As such, I don't delve into the proofs of theorems, nor do I go into excruciating detail with examples. If you've never had a full course in trigonometry and you're currently in a pre-calculus course, I highly recommend watching my trig playlist on YouTube, as it goes into greater detail with all of the concepts in trigonometry. Again, trig is so important for calculus that having a shaky background in the subject will lead to abysmal results in calculus. With that being said, let's talk about applications involving non-right triangle trigonometry. And this is listed as part 1 because we're going to only use the law of sines here. The second part, we will have the law of cosines at our disposal. But for right now, law of sines is all we need. So, observers at point P and Q are located on a side of a hill that is inclined at 32 degrees to the horizontal. The observer at P determines the angle of elevation to a hot air balloon is 62 degrees. Simultaneously, the observer at Q measures the angle of elevation to the balloon to be 71 degrees. If P is 60 meters down the hill from Q, find the distance from Q to the balloon. This is a very, very complex sounding problem, but we've read it. Now we just need to really truly draw a picture so we can actually understand what's going on. So I've drawn my horizontal, and we have a hill that's inclined at 32 degrees. So let's go ahead and just put in a hill at 32 degrees here. There's our 32 degree hill. All right, to there. Great. And we have two observers, and let's see the distance. I'm reading through, sorry. P is 60 meters down the hill from Q. So P and Q are 60 meters apart. I'm just going to plot Q first. So Q is uphill from P. I'll use blue to plot Q. So I'll say Q is right there. And the angle of elevation from Q to the balloon is 71 degrees. That's this piece right here. And the angle of elevation for observer at P to the balloon is 62 degrees. And so there's a lot going on here. I just want to kind of highlight the big deals. So the angle that the incline is 32 degrees. So we already done that. You saw me measuring that out actually. The angle of elevation for the visual observer at Q is 71 degrees. What does that mean? It means that if Q was to look horizontally, then look up through an angle at the balloon, that angle would be 71 degrees. It's not that if the observer at Q was looking in this direction and then looked up, that's 71. It's from the horizontal. Same thing with P. The angle of elevation to the balloon for person at point P here is 62 degrees. And so if the person at P was to look horizontally, they would look up through an angle of 62 degrees. That's just an important piece of information here. And then the distance between them. So I'll use orange for that. This distance between them was told to us to be, 60 meters. So I'm gonna write that down. A little bit tough to write in there, so I'll just point an arrow and say that's 60 meters. So now I know, and by the way, there's a balloon up here, I'll call that B. And we want to know what's this distance D, the distance between the person at Q and the balloon. Now that's a picture of the situation, but that is really, really tough to work with in a, in a drawn situation like this. So generally I like to draw a picture just to visualize the situation. And then I actually take the triangle out of that picture and I walk it down here. I'll use the same colors, but now I'm going to freehand this. So here's my freehand drawing of this. There's the side length D. And then my orange side length. And I'm going to over accentuate things just so that I have room to think, really. So that'll be a side length of 60. And then we have this red side length here. It's just to get me away from all the busyness of this stuff. And I guess I could label this as point P and the other one as point Q. I understand if you look at this that you're going to say, well, that's the same triangle. Why'd you redraw it? The main reason why I do that is because there's a lot of extra thinking that's involved here. For example, this red angle of 62 degrees, I hope you would agree that's not this angle. That blue right there, that is not 62 degrees. So how do we find that interior blue angle, which actually I should just draw as red? How would I find this angle right here? Well, if I'd stuck with the original drawing, it'd get super duper messy. But we know that this part of the angle from the horizontal is the same as this angle right here, 32 degrees. So if that's 32 degrees, the rest of this angle right here must be 30 degrees. Again, 32 degrees was the first chunk of this angle, and then the remaining was 30 degrees because the total is 62. So I know that this angle right here is 30 degrees. Notice how much cleaner it is in this drawing than the drawing above. I'll do the same thing for angle Q, although angle Q is going to be a little more challenging. Again, the angle with the horizontal here is 32 degrees because that's the same angle as this one right here. So we know that the remaining angle is 71 minus 32, which is 39 degrees. But does that give us the angle we want? No, it doesn't. We actually want the interior angle, this guy right here. Well, if you take a look at that 39 degree angle versus this, I'll call X degree angle, they are supplementary angles. And so therefore, X plus 39 degrees should equal 180. That is, X is going to be 180 minus 39, which is 141, I think. 141 degrees. I didn't need the degree sign on there. So 141 degrees is what that interior angle is. And notice the reason why I didn't want to stick with that original drawing is because it's an absolute mess now. But this drawing that I have here down below is actually very clean, super clean. Now I can go ahead and build my table and just talk about what are these missing things that we need to find. And maybe I should not have labeled that D. I should have labeled that lowercase p, although my lowercase p looks like a capital P. But there we go, lowercase p. Here's the lowercase q, which I'll draw in blue. And I think we called the other side angle B, so that we'll call this side B. And so now I'll make my table. Our table will be angle B, angle P, angle Q, and then side B, side P, side Q. How's that? And we were given that angle P is 30 degrees. We were given that angle Q is 141 degrees. And we were given side B is 60. And you don't see a full row. And you think, I guess I can't use law of sines. But actually you can complete this row because you have two angles in a triangle already. So 180 degrees minus the sum of those two angles will give you this 9 degree angle. And I'll write that in blue because we computed that, but that's just to tell you we can easily get that. And now I can use law of sines. Remember what we're going for? We want to know what side P is. So I'm not going to bother with Q. I'm just going to find side P. Side P is to the sine of its angle, P, as side B is to the sine of its angle, 9 degrees. Multiply both sides by the sine of 30, which is 1/2, and you'll get that P is 30 over sine of 9 degrees. Again, I multiplied both sides by the sine of 30, but sine of 30 degrees is a half. So a half times 60 is 30. And now I can just go over to Desmos, and I don't need to showcase that. I'm just going to type it in. And I get 191.8. That's rounded to the nearest decimal place. Let's see what they ask, actually. They do not ask, actually, for rounding. So you might actually want to round to the nearest whole number. Maybe. Because they didn't give us anything with decimals, so it might be nice just to keep it as 192. So the distance between the person at Q and the balloon, which we were calling P, actually, is approximately 192 meters. There we go. There's a good law of sines application with some strong advice on redrawing your triangle, because when you draw the initial situation, it's going to end up being a mess. So it's probably better to take that triangle out to make a better looking triangle outside of that. And just because we can, let's just do one more. Even though most law of sines applications are kind of the same, it's good to see a couple of them. So you have a shortwave radio antenna, and it's supported by 2 guy wires. They are 165 feet and 180 feet long. Each wire is attached to the top of the antenna and anchored to the ground at 2 anchor points on opposite sides of the antenna. The shorter wire makes an angle of 67. How far apart are the anchor points? This is a basic graph of the situation. We have the shorter wire, which I put in red here. That's 165 feet long. The longer wire, which I put in green, is 180 feet long. And let's see, what else? The shorter wire makes an angle of 67 degrees with the ground. So that red wire makes an angle of 67 degrees. And we're asked to find the distance between these two. Now, technically, you could definitely do this problem using right triangle trigonometry. However, it's better that we just practice our law of sines. Now I'm going to go ahead and label everything because, well, I can. And I'm just going to use the letters A, B, C. That's angle A. I'll call this angle B, and I'll call this angle C. And remember, I like to use capitals there. And so therefore, this is side A, this is side C, and this full side is side B, and that's the side we want to find. Again, you could do this problem, I'm going to erase that, but you could do this total problem with right triangle trig, but that's a rarity. That's just something that I'm just letting you know you could have done, but we're not going to assume that for right now. Let's just go ahead and do law of sines. So here we go. I'm going to draw out my table here just down below. There we have it. And I'll highlight the fact that we have a full row. There we go. We have a full row, which means I can find this angle C by comparing that full row to that bottom row. Remember, we're trying to find side B, so this is going to be a full problem. There's just nothing we can do but go through this entire problem here. So this is going to involve the ambiguous case because we're finding that angle C. So we have the sine of angle C is to the side C, as sine of angle A is to side A. I was just double checking that the side A was 180 feet because that was just putting up red flags for me, but that's okay. So this will imply that C, angle C that is the sine inverse or the arc sine of 165 sine of 67 degrees over 180. Notice the feet cancel. So I will go ahead and let's go over to Desmos and do this computation. And I typed it in here. You could see that I'm saving the result just in case. So 57.5, I'll round to the nearest decimal. So here we have approximately 57.5 degrees. I'll just write that in here, approximately 57.5. And that means that our angle B will be also an approximation. And all I did here was go ahead and just say angle B is 180 minus the given angle of 67 minus our computed angle of C. We get 55.5. So I fill that in, and note, we really want that last thing there, which is the side B. Now, I do want to mention, because we had used the law of sines to find that angle, I would say check normally for second triangle. And I think it's probably a good idea to go ahead and just do that anyway, even though I'm going to guarantee you it's not going to happen. But let's finish this out first. You always finish out a single table first and then go back through and check for that second triangle. So let's go ahead and finish this out. Let's see, side B, I'll do this in a different ink. Side B is to sine of angle B, as 180 feet is to the sine of 67 degrees. And this will imply, I'll zoom in because it's just easier, 180, B is 180 feet, sine of B over sine of 67. And I'm going to go ahead and go over to Desmos to use my as many decimal place version of B as possible. And you can see we get 161.1. Let's just keep it that, 161.1. So I'll go ahead and fill that in. B is approximately 161. Actually, I'll just say 161 feet, just because they didn't hand us anything in with decimals. I don't want to answer with decimals if I can help it. Now, I should say we need to check for that second triangle. And when you check for that second triangle, it's really very fast. You don't need a calculator for this. When you check for a second triangle, all you're really doing is taking the angle that you computed initially, the 57.5 degrees, and you're looking at its supplement. That's 180 minus the 57.5. That'd be what, 122.5 degrees? So I'll just write that down. Again, these are approximations, but we can deal with these. And we're going to just ask, could we have, instead of having that 57.5 degrees, could we have had 122.5 along with the given 67 degree angle? And the answer to that is definitely not, because this angle, 122.5 degrees, plus that 67 degree angle that we were given, that's greater than 180 degrees. That's more angles than we have in a triangle. So there's no second triangle. So only one triangle. And that's a really fast check. And usually in applications, you're not going to have a second triangle, but it's not always going to be the case. So you should check. And that's the answer, by the way. The answer was 161 feet. So that is the distance between those two anchor points, roughly 161 feet. There we go. So those are some applications involving law of sines. I hope that is helpful.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at ease. Says, listen close. Don't talk too much that isn't kosher. You may really hurt inside. It doesn't justify you to speak too loud and cry.